Okay, so let's move forward.
Hello?
So we are here with Alessandro and Juan Jose. There are CTO and CEO of Osmium. They co-founded Osmium, and they are here today to presenting us securing space networks. So thank you a lot. Stage is yours.
Hello. Do you hear me? Yeah. Okay. So he will speak about the interesting stuff on security. I will briefly introduce Osmium. We are a cybersecurity company. Our focus is the resilience of embedded system for aerospace and defense. And we are working basically on different areas, which include, maybe I move, which include cybersecurity engineering for space and aviation. We have customers both in the space and aviation industries, and we have also a strong background on space networking, which is basically the topic that will be treated today. We are also one of the 12 founding members of the European Space CYSAT, so we are very happy to be an active contributor to this important initiative for the industry. This is just to show some of our customers and partners that we have been working recently, and also the ones that have, let's say, help us on the incubation and the acceleration process that we are doing with the ESABIC, with the National Cybersecurity Agency from Italy, and with the National Cybersecurity Agency from Spain, that has allowed us to develop one of our solutions, which is a secure operating system for embedded systems. The topic today that will be treated by Alessandro is related mainly to work or activities that we have conducted for ESA in the last years, but also some projects that has not to do with ESA, but relates to, in any case, to the security of inter-satellite links, and in particular, the security of disruption-tolerant networking, and in particular of BPSec, of bundle protocol, using BPSec and bundle protocol security. And also we will touch at the end a little bit something about the satellite project, which is a project in which we are prime, and we are working on a lightweight implementation of a key exchange, post-quantum key exchange for satellite communications. The next one. In this area, so we have the opportunity, and this is what it will be presented, of working on two papers. So we have a strong background, let's say, on the capabilities to work on research, and we have presented two papers. One was a journal that was presented recently by the end of last year, and this is what Alessandro will be explaining now. So, please, Ale.
Thanks a lot, Juan. Sorry, I come here. It is better. Just to say briefly that this presentation will be slightly different, maybe from what we saw, because it was a bit futuristic some years ago. Now it is really getting more and more actual. So we will speak about DTNs, so disruption-tolerant networks, and ways to protect them. So actually, what we did, I don't know if you see the laser is not working well, but what we did was we investigated the RFC and the protocols available to deal with these networks, and we identified the threats that these networks can suffer from. Then we analyzed the capabilities of the current protocols to cope with those threats and risks. For this, we propose 4 different security models that are trying to consider both simple cases in which a single network is considered, but also more complicated cases in which heterogeneous ones are being taken into account. For these use cases, for these security models, we have run some simulation considering a constellation of LEO and also a constellation of LEO plus GEO. Let's see. Okay, so let's set a bit the background of our research. This this research has as a, let's say, a background the space information networks. These are completely independent networks from the standard terrestrial ones, and they represent a paradigm shift in global communication infrastructure. So here we are really using different heterogeneous space platforms. So LEO, MEO, GEO, but also high altitude platform stations. And this heterogeneity extends beyond the technological domain. So it is not just using different technologies, but here different operators should coordinate with each other to deploy and manage this complicated network. So it is clear that the problems from the standardization point of view, but also compatibility and security are pretty important. So the nature of these type of networks is intermittent by, let's say, there's no the classical continuous connectivity. So two nodes might see each other every minute or every hour. So you cannot really rely on a stable connection. And it could be the case that a node is isolated even for some hours. So some examples of these networks are the solar system internet and also the Moonlight program. All right, what was proposed to cope with this, let's say, networks is the bundle protocol. This has evolved over time, and now we are at bundle protocol version 7, and this bundle protocol relies on underlying transport protocol. So it runs on TCP or UDP, but also on space protocols. So here, differently from standard protocols, we are not encapsulating the message within another layer. So it is not the classical ISO-OSI stack approach. Here we are augmenting the message by introducing additional information. So we can distinguish here in this picture the most important parts of a bundle. So we have the primary block, which includes all the metadata to route the bundle from the source to the destination. Then we have the payload, so the message itself. And we can have additional extension blocks that bring some additional information like the previous node, bundle age, and the hop count. And to protect this type of, let's say, bundle, the BPSec, so another protocol, has been introduced, and this reuse the same approach. So it adds another block to secure some other block. So I know that is a bit, let's say, recursive, but here you can see a red block which is pointing to other blocks to protect them. So this security block in this case can, and here we will see some example, can be a beep, a block integrity block, which includes a message authentication code or a signature to protect the target block. So in this case, we can protect the primary block using this beep, or we can have a block confidentiality block, or BCB, that can encrypt another block. So in this case, we can encrypt the payload. And the bundle protocol security defines 3 roles. So each node in the network can play 3 different roles. A node can be a source, meaning that can add a specific security block to the bundle, or can be a verifier, so it is not modifying the structure of the bundle, but just verifying that nothing malicious is going on, or can be an acceptor. So the acceptor is the node in charge of removing the security block. So differently from the standard, let's say, classical networks, in which we always try to have the end-to-end protection in place, here we need to think about something maybe different, because we will see in the later phase that maybe the end-to-end approach is not really the best one. So it really depends on the risk sometimes. So what is not defined by BP and BPSec is how to define the policies. So we know that we have 3 roles. But we know that we have these 2 blocks to protect our bundle, but we don't know who should add a security block, who should provide an encryption, who should remove the encryption, right? So this is one of the aspects that we addressed and we have tried to understand more. So just to recap a bit what is bundle protocol and bundle protocol security for those that are not really into the DTN world. So let's suppose that we have 5 nodes from A to E, and let's suppose that we want to, for some reason, protect the integrity of the primary block from the source to the destination, while for some reason, and let's suppose that node A and node E do not have the keys to also include additional protection. So, but there is the need to protect also the confidentiality of the payload from node B to node D. Maybe we are crossing an untrusted network. So let's consider this case. So in this scenario, the node A will be the source of a BIP, so we'll be protecting the integrity of the primary block. Then this will be sent to the node B that will play 2 different roles. So it is possible to play also multiple roles. So this is where the security policy comes into the game. So here we need to decide which are the actions that each node should do. So here the node B first verifies the BIP, so checks that the primary block has not been tampered with, and maybe then it plays the role of the source. So here we see that a BCB, a block confidentiality block, has been added, targeting the payload. The payload is encrypted, and all the data, all the parameters that are needed to decrypt later on the package are included in that BCB block. So now the bundle is moved, is transmitted to a node C, which maybe just play the role of the verifier. And let's suppose that it is just checking that the BIB is successfully verified. So the primary block has not been modified. Then this is sent to the node D. Here, again, we can play the role of verifier, so we can check that the primary block has not been modified, but we can also accept the BCB. So here, as you can see, the node is removing the block, decrypting the payload, and pushing this to the final destination, where the BIB of the primary block will be accepted. So this was really to, in a nutshell, to see how potentially a bundle protocol work along a path. So in this slide, on the left, I included some rules, some constraints that we have to work with when using BP and BPSec. So these are important, but I will not go into the details, otherwise it might get too boring. So maybe just the first line is about the BIB. One limitation, we can say, of the BPSec is that you cannot apply an integrity protection on something which is encrypted. So in some cases, it could be interesting to do that. But the other ones, the other rules are, let's say, different, but still needs to be applied. On the right side, instead, I think it is important to see that bundle protocol security provides additional tools to protect in a more holistic way the bundle. So let's suppose that we have a BCB, so at the bottom, and here the BCB is encrypting the target. So here we are encrypting the payload that is here. So what might be needed is to connect this confidentiality protection to an integrity protection. And this is actually what BPSec is providing. So the RFC 9173 tells or imposes to use authenticated encryption algorithms. In this case, we are using AES-GCM, so we can not only encrypt the payload, but we can use the additional authenticated data to link the protection to the security header of the bundle of the BCB itself, to the payload header, but also to the primary block. So to some extent, we are protecting the integrity of the entire bundle. All right, let's now jump to, let's say, the security models that we investigated. So here we assumed m different networks, so operated by a different operator, sorry for the repetition. Each of them is composed of n nodes, and in this model we can assume that within each network, each node has the key material to communicate with another node inside the same network. Instead, when we have to cross the boundary, we have these special nodes called gateways that knows how to communicate in a secure way with other networks. In this setup, we consider 4 different security models: the end-to-end, hop by hop, edge by edge, and edge to edge. So for this, we have analyzed the security policies, and we performed some evaluation of performances. So let's start from the very first, let's say, security model. This is the classic end-to-end scheme in which, we are, let's say, implementing end-to-end the security. So here the source is including a BCB that, as I told you before, can be extended to also to cover the integrity of the entire bundle. And this is then sent over the path till the very end. So the final destination node will accept or resolve the BCB, will decrypt the bundle, and will pass the bundle to the application layer. But this in DTN is really complicated. As I told you at the very beginning, here we need to consider different operators. They need to speak with each other. So in this case, if we want to implement this kind of approach, we need to have practically each node should have a key for each and every other node of this extended network. So that it is impractical. So another, let's say, drawback of this approach is that an attack going on the path might remain undetected for a long time. So here you can consider that a single hop might take minutes or even more. So you are storing bundle that potentially has been tampered with. So you can easily perform a denial of service on DTN networks. So this might not be important maybe in a military use case where the confidentiality is more important, but for other use cases, this is actually a big deal. So another aspect is to mitigate this kind of attack. We can add, as I did in the previous slides, we can add a BIB, so an integrity block protecting the primary block. So in this case, we can mitigate threats, spoofing attempts, and diverting the bundle. So using a BIB can be used for this purpose. The second model is the hop by hop. This has been, let's say, investigated just to compare the different options, but we know that it is really not practical also, this one, because it is complicated from the key management perspective, and we would have also different attacking points that can be used to tamper with or manipulate the bundle or simply eavesdrop the communication. So, but a good part of the hop-by-hop security model is that any attack would be immediately detected, because at each hop we are decrypting and recrypting, decrypting and recrypting. So every step is, each node is checking that everything has been correctly sent and has not been manipulated. Then we start with the most interesting security models. The first one is the edge by edge. So here, the security policy, the security process in general is managed differently when we switch from one network to the other. So as you can see here, the gateways are interrupting, let's say, the security line, because there is these gateways are using a different key when we go outside their their network. So in this case, we can, in this model, we can think about using pairwise group key, and this would limit the number of keys that are needed for the end-to-end communication. And the last one is the edge-to-edge scheme. We can see this as, let's say, an evolution of the previous scheme. So here, the security is managed only in the initial or the source network and the destination network, and in particular by the source gateway and the destination gateway. So here, we avoid to have security activities in intermediate nodes, and also in this case we can include additional protection by adding a bib on the primary block. So we simulated this. I will check also. Okay, yeah. We simulated these cases in a Leo constellation and Leo plus Geo constellation, and in this simulation, each node was generating randomly 10 bundles by having at the end 480 bundles for each simulation. And as I told you at the beginning, we simulated this over Leo constellation or Leo plus Geo. So this is just the extension of this constellation by adding 3 Geo that are providing continuous connection. Let me say that differently. Each Leo satellite has a minimum a Geo satellite inside. So there is always this Geo as a possible next stop. And in these cases, we analyzed the number of operations, security operations that are needed, and also the detection steps that are needed to, in case of attack, we need to go through to check that something malicious has happened. So shortly, we can see that the end-to-end scheme is the one that, of course, has less security operation, but on the other side is the one that requires, that it takes more to detect the security attempt. So this is, let's say, it for the DTN side, the DTN part. I wanted to have a bonus slide about PQC, also to speak a bit about the project that Juan introduced at the beginning. So this is the satellite project in which we are, let's say, revisioning the IKE version 2 protocol to make it lightweight and post-quantum. And I saw before that the BST guys presented a very good, they did a very good presentation about post-quantum. So this was supposed to be just a bonus slide in which we can visually see which are the main differences in terms of size and their impacts on the communication. So let's suppose they're very at high level. So let's suppose that we want to protect a key. So we are practically creating a session key. So this is typically a 256-bit key, and we can use different cryptographic primitives. So we can use the ECC, which is maybe very small, and also, maybe also resistant to PQ. Then we have the standard classic RSA, and then we have the new Kyber that it has been selected and so on. And in this example, we wanted to show you also that there are other options like make a list that, as you can see, is very, very big. So here the private key is bigger than the sum of all these other keys. So, and what is maybe surprising is that as an output, we will have this type of encrypted form. So the RSA will create an encrypted of the key of 920 bytes. The ACC will be very, very small. Kyber will be close, let's say, to the RSA. And surprisingly, the backlist will provide a very, very small encrypted ciphertext. So maybe in some case, this can be used. So, but here, there's something wrong. I mean, if we want to take the communication perspective, we don't really need to check the size of the private key. Instead, we need to check the public key, because the public key is the one that is being sent and communicated, not the private key. So in this case, if we look again at the picture, we can see that the public key of McAleese is even larger, is even bigger, but actually, to make things realistic, this would be the size. So all the private keys here are, this is the relation between the private keys that we saw before with the public key of McAleese. So you see that we have a giant here, half meg of key that can be used. So this is just something that I wanted to show to you before closing my presentation. Thanks a lot.
Okay, so thank you a lot for everything. Do we have questions? Okay, I start with a small question. What about managing routing in the protocol that you showed us? So what about dynamic topography?
Yeah, that's a very good question. Actually, in DTN, it is a matter. So given the intermittent, let's say, characteristic of the DTN, doing the routing could be complex, and also doing secure routing can be even more complex. So there are a couple of papers that are dealing with these topics, but it is still pretty new. So we tried, we are also investigating on this to let's say, create secure routing schemes.
Do we have other questions? Please.
Yes, thank you very much for the presentation. I have a question. Which model would you recommend between the 4 you presented for ISL LEO Geo and for large LEO constellations such as Starlink, for example?
Yeah, very good question. This really depends on the use case that you want to address, because as I've tried to summarize, each model has pros and cons. So you need to deal with them. So there's no, maybe we can consider the hop by hop as the worst one, but all the others can be good. So if possible, depending on the latency and the degree of intermittency, you can use the end-to-end. But otherwise, you need to go in between, and you can go to the edge-to-edge. That maybe it is a good trade-off between the 4 models.
Okay. So thank you a lot one more time for your presentation. Thank you.
Thanks a lot.
Thank you.